So this is a session on crowdsourcing, and what's a paper on multicast doing in the session? And we can try to blame James and other organizers, but if you look at the sessions carefully, there's really no place this could have gone. Okay, so it was going to be out of place anywhere. There's a session on networking, but it meant social networking and manufacturing networks. The fundamental question was asked by one of the reviewers. They looked at my references and said, only 2 papers in the last 10 years in the rest of references, and they both involved me, and they're actually very loosely related. So I had to spend a lot of time saying, why am I, going back to the future, or why am I doing this dated work? Motivation comes from a course on collaboration I teach. And here's the list of assignments that my students have to do. And the one way to do these assignments, so the question then was, what kind of distributed infrastructure should these students use for their assignments? And they can use some inter-process communication mechanism. Okay, we heard from Tommy's talk that WebSockets could be used or HTML could be used. And, but, if you think about it, all IPC mechanisms provide is 2-party communication, whereas in collaboration, there's group communication. Okay? And there's also they are not arbitrary group applications. They're a narrow range of group applications. So we should be able to use higher level infrastructures, and such infrastructures have been built. So the question for me was, how suitable are they for the assignments I have? Okay. So actually, I'm going to put the pointer on also, just in case. To answer that question, I need to give you an idea of this is actually an echoing program. You can enter what you want to be echoed either in a GUI or in the console, and it'll keep a history of everything you've entered and display them in both UIs. Okay, so this is a multi-view application. Okay, and also it has, to make things interesting, it has an editing component that you can a field you can edit. Is to make this collaborative, and our echoer suddenly becomes an IM tool. Okay, and we can also collaboratively edit the text string, so it also becomes a collaborative text editor. This is shared model rather than shared window, and you can see that the window sizes are different. The cursor here is not following the cursor here, so this is view divergence or shared model. If you want no view divergence, you can use a shared window system, which is kind of like screen sharing, except that you are dealing with window API rather than with bits, with pixels. So you don't have to worry about different computers having different density of pixels as Tommy had to worry about. But otherwise, it's very similar. And when you have window sharing, you can also have a telepointer because it will point at the same location in all windows. So syntactic telepointer works. And window sharing is also application independent. You can use it not only for this, but for some arbitrary other tool. And this picture shows you another couple of issues. When you're interacting with a collaborative application synchronously, you have to worry about latency. Latency becomes a particular problem when you are using a telepointer. And you see here that this particular user is behind these 2 other users. Okay? So there's latency. Often latency is accompanied with jitter, and interpreting remote gestures becomes tricky when there's jitter. And Carl Goodwin provided a solution to this problem, where he showed the past history of the telepointer, not just the current telepointer position, but a whole trail, and that can be used to figure out, for instance, what the other collaborators are circling. Okay? So that's another project for my class. In this example, if all interaction stops, there will be eventual consistency. Okay? So that's good. Okay? And here's an example. Alice types. Okay? What Alice types is seen by Bob. Okay? Because the latency from Alice to Bob is small, but the latency from Alice to Kathy is very large. So Kathy hasn't seen this as yet. Bob, on seeing Alice's message, so Kathy hasn't seen this. Seeing Alice's message response, That response is seen immediately by Kathy because they are connected through a faster network. And now we have diverged. Okay? And Kathy is confused and is trying to go and fill in parts of the poem that haven't been entered. Okay? So this is non-causal. And what you want to do is causal, where when a message comes in, you look at its timestamp, a logical timestamp, discover that something earlier hasn't come, wait for that to come, and then go and display the messages out of order in which they were received. Okay? So that's another project. How this works is not important. What's important is that you have to do some kind of filtering and massaging of the messages to make this. Okay? Even trickier is concurrent input, okay? Where you see here that 3 people have entered 3 different things at the same time, and if you're not careful, this in IM tools, they'll get ordered differently at different sites. Okay? Maybe in IM it's not so bad, but there are all kinds of misinterpretations that can happen even here. Shared editing task, it's considered really bad because here you have 3 users who have typed the same character at the same time. Your shared document now is different in each site. Okay, so this happened because we weren't using operation transformation. If you use Google Docs, they have an operation transformation algorithm that makes sure that this doesn't happen, and that is one of the projects for my class. Okay, and consistency can be done through operation transformation, or it can be done through locking. And you have now a locking assignment here that allows you to request locks, release locks, and these operations can happen implicitly in response to user actions. Okay? So in my class, I'm sure many of you are happy you're not in my class at this point. And the question again is, and this is the details. Let's go and abstract out some of the requirements from these assignments. So the IM editing tool requires model sharing. Okay? Operation transformation also requires model sharing. You have to know about the text buffers and insertions. You can't deal with mouse movements and character types that don't have the full semantic information. The Windows assignment involved window sharing. The telepointer trails in JITTER also was involved with telepointers, which required window sharing. And the other ones could be done using model sharing or window sharing. Okay? What you're sharing is one dimension of collaboration. Another dimension is the application architecture. Is the application replicated or is it centralized? If I'm sharing a PowerPoint, does everybody have a PowerPoint on their computer, or does one person have the PowerPoint and everybody's just following that PowerPoint? Okay. Causality is an issue when you have replicated architecture, not when you have centralized. Same thing with operation transformation. If you're going to do locking, you've got to have some centralization to make locking work, and so you're dealing with both centralized and replicated architectures. And in other cases, it doesn't matter what the architecture is. You can do it. You can do the problem with either architecture. Okay, with some consequences on performance. That's the application architecture. There's also communication architecture. When 2 sites have to communicate, do they communicate directly or through some intermediary? Okay, a relayer. Causality is an issue only when you're communicating directly. If you're communicating through a relayer, then you will see the same sequence of messages. The Google Docs algorithm that I talked about for operation transformation assumes that communication is relayed. Okay, and that's the one they have to implement. And so we've got this requirement of supporting both direct and relayed. And in the other cases, you could go either way. If you remember the telepointer trails assignment, the telepointer movements were buffered, okay, so that you could show a trail. That means the messages that arrived were massaged, were filtered in some way before being presented to the user. They weren't presented as they arrived. Okay, same kind of thing happened in causality. They were timestamped at the sending end. The timestamps were looked at the receiving end, and they were reordered. Okay. Operation transformation, again timestamped, and in fact the operation is transformed at the receiving end. So there's filtering to be done at the sending and receiving ends, and in the other cases it's just unfiltered. Okay. As I showed you with the window-based example, you could have multiple applications being shared in the same session. Okay? And that makes sense. You know, any practical system is going to allow you, including Google Hangout and Live Meeting, are going to allow you to have a chat session and a video conferencing session and a shared editing session, all in subsessions of a bigger session. Okay? So you need to be able to support multiple sessions. Okay? So here's a list of the requirements for my set of assignments. And the question is, how well do current infrastructures support this? Okay, like I said, IPC will support it. It's very general, but it's almost, it's arguably impossible to implement all of these things in one semester using just IPC. Okay, with shared model and shared window systems, by definition, one system can't do the other. Okay, so you can't have shared model and shared window with those two kinds of systems. So we are left with group communication. They are lower below shared window and shared models. Okay, but the current group communication systems are bound to a particular application architecture. They assume either centralized or replicated. They are bound to a certain communication architecture. They typically assume direct, and they don't provide any support for filtering. Okay? And they don't support, even though practical systems provide multi-application sessions, the abstractions that have been developed don't. Okay? So we have some, in this design space, we have some gaps to fill. Okay? But are these gaps artificial? I mean, I'm an academic. These are all assignments from my class. So, does it matter in the real world? I'm showing you some practical system available today, in use today, that actually meets that requirement. Okay? So they're not artificial. And sort of one consequence of this is that, in the paper, I don't refer to these systems in the paper because they don't have any research papers I can refer to. The API keeps changing. But I have looked at many of these. And I can say that this is what happens today. Who knows what's going to happen tomorrow? But one consequence of this is that based on my understanding of Google Hangout and Google Docs, you can't use Google Hangouts to implement Google Docs, okay, from the same company. Okay, so this problem that I'm trying to solve is not just an academic. So how are we going to solve the problem? So I'm going to start with inter-process communication and show you how we can put layers on top gradually to meet our requirements. Okay? So that's what I'll do. I'm going to assume a very simple model of inter-process communication where you have a send call that takes a host as an argument, a port as an argument, and sends a message to that other end, and there's some way to receive that message, maybe using a receive call. Okay? And let's go and see how we can first use this call directly to implement some of the assignments, and what are some of the problems that arise in terms of implementation, and how we can do better. So I've given this kind of assignment many times using just asking students to just use IPC, and this is what they do. They basically, when a message has to be sent from one user, some activity occurs at one user's end. A message goes from that user to the application. The response comes immediately. Okay? That's that's typical of collaborative applications. And then that message is sent to all the sites, to all the other sites that need to see it. Okay? Somehow, this particular site had to know the host and port numbers of this site, this particular application, and this application. Where's that information? That's provided by the session manager. Okay, so all of these applications join the session manager, and they provide their data about their ports, etc., which can be fetched and used for communication. Okay, so that's typically what students do if I don't give them any extra layer. Okay, and in this picture, the communication was direct. That the IM tools talked directly to each other, and have it send the messages to other people. Okay? Again, this is something students have done in the past, in past offerings of my course, and to this situation, well, I can provide them with a generic session manager that can support both relayed, that can support discovery. Okay, it can support relayed communication, and it can support discovery of other clients. So that's one way to now add to the abstraction. And and the applications needn't go through the generic session manager to do the communication. They can talk directly to each other also. Okay? But they must be changed to support P2P. Okay? So when they're using generic session manager, they have to use one set of primitives. When they're communicating directly, they have to use another set of primitives, and that's a lot of work. Okay? In fact, never has a student of mine done both things in one assignment when they were using IPC directly. Okay? That was a barrier. So what we can do now is not provide just a generic session manager, but we can replace the IPC layer a group communication layer. Okay? So now the group communication layer is not between 2 points. It allows communication among groups, and so there's a local library at each site. And now when an activity occurs, a message is sent to the group communication layer. It's not the send call that we saw earlier. It's to others. Okay? It says everybody else in the session, okay, except me. And so the application, the layer can then go and send the message to all the other sites. And this is application level multicast. The application delivered one message to the communication layer, but it went and delivered multiple messages to the network layer, okay? Which is different from network level multicast, where one message is delivered to the network layer, which can then make multiple copies or send only one copy, depending on what the syncs of that message are. Okay? And in this case, the message was sent directly. What we can do is, and that happened because when this particular user joined, it said that I want direct communication. Then the two others call doesn't have to change, and it goes now through the central process. Okay? So now in the same assignment, you can do both kinds of communication. So this is important. The call is unaware of specific users in communication architecture, and we have the one dimension of the flexibility we wanted earlier. Okay? So two others is one multicast group that's defined by the library. What are some other possible interesting multicast groups? We can send a message to everybody, including ourselves. Okay? So when an activity occurs, we don't go and respond to that activity directly. We send the message to the relayer, and it goes and sends a message now to everybody else. Okay? And this is important if you want total ordering of messages. You can also send a message to a specific client. Okay? So this is now you're getting a little aware, but you're just naming the user. You're not naming the host and port number, and so the message goes only to that particular client. And this is very important if you're going to do the centralized architecture. Okay? So in this picture, the way the join call is architected, there's only one session in the world. Okay? Often, so you sometimes want multiple sessions, and you want, for instance, one set of users to do an IM, another set of users to do another IM, and that is supported by having another argument that takes the session name so another argument to the join call, which is the session name. And now suddenly the join call has become an access controlled operation. Okay? That only certain applications may be able to join certain sessions. Okay? So it shouldn't be the case that an arbitrary person can join my IM session. So that's multiple independent sessions. Sometimes you want dependent sessions. So this is a tool that when I was at Microsoft, we built extension to Visual Studio, which allows a team of engineers to go and collaborate with each other while developing the program. Okay? And in this case, Alice can go and start a text chat or a code share or an audio-video chat with her collaborators. Okay? These are not three independent sessions. They are dependent sessions. Set of possible users in each of these sessions is the same. And if Alice is allowed to join or view text chat, she's also allowed to join the other ones. Okay? So you need to somehow link these sessions. And this is the abstraction that allows that to happen. So now in a session, not only do you have you have users and users directly in the session, and you have applications in the session. Each application in turn has a set of users. So each application defines a subsession, and the top level session defines both applications and users. Okay? And so in this case, Alice and Bob are using IM. Bob is using editor with nobody joining him, and we can now have Kathy. So how do we support this? We extend a joint call to not only take session names but also take application names as arguments. Okay, and what does this call really mean? Let's look at it. Let's look at that through an example. It means that Kathy wants to join the session. Okay, plus Kathy wants to join the IM session. If Kathy again makes a call, this time with editor, Kathy has already joined the overall session, so Kathy just joins the editor session at this point. Okay, you can also join a session without joining any application session. So David is joining and doesn't give any application name. So basically, David snoops on the session, just seeing who's in the session, who's not in, what sessions are active, and then based on these parameters, he can then go and decide to join a particular application subsession. Okay, so that's what's happening here, and now we have our requirement of multiple subsessions. Okay, now whenever you talk of distributed computing, you should worry about whether you're going to support synchronous or asynchronous calls. Okay, and if you want the kind of assignments I showed you, you really need asynchronous. Okay, and let me show that by contradiction. Suppose you have synchronous, what would that mean and why would that be bad? So a message is sent, generated, the message is received at the other end, that an ACK is generated to know that the other end has received it. An ACK is received at all ends, and when all these ACKs arrive, at that point, the next message can be sent. Okay, that can take a lot of time. Okay, how much in practice? Round trip times can be, we don't all have Tommy's high-speed network connecting all the users together. And even if we did, say you're in Australia and I'm here, there's an Australian researcher who makes this point many times, the speed of light is going to be an issue in causing problems. Okay, so if you're just doing telepointer movements, I've done some measurements, and the time between telepointer moves is as low as 10 milliseconds. Okay, so you can see how the 10 milliseconds is being expanded to 2,000 milliseconds at the other end. Okay, and so that can, and the tolerable and noticeable times are very small, so that can be a real problem. Okay, operation doesn't complete when it's issued; it completes later, and you can discover the completion by callbacks. Okay, so when you make a join call, at some point you can be told you've actually joined. When you do it to others, at some point you can be told that this particular, at this end, you can be told, of course, in our system, you never get to know at the sending end whether the message really arrived at the other end or not, because it's guaranteed to arrive. And but the receiver gets an asynchronous call. Okay, I'm running out of time, but I think I have only 6 more slides to go. So let's talk of filtering. So here's a message that is generated. It's given to the group communication layer. It goes unfiltered to the other group communication layer, and it goes unfiltered now to the user. Okay, same thing with another message. Filtering, a message generated at one end can be massaged at the local layer, so it becomes a different message. And same thing with the second message. And then at the receiving end, these messages can be delivered in a different order. Okay, so message 2 is delivered first, and they can be changed. Okay, so how do we support that? Well, in this case, what's really happening is that the group communication layer is doing the filtering, and the send and receive layers are filtering unaware. Okay, so that's what's happening. But filtering is application specific. So how can we do both? Okay, well, it really means that group communication has to be extendable. And here's how it's extendable. The sender makes a call to some part of the group communication layer that says, please send the message. That layer does various levels of processing with that. At some point, it goes and calls an application callback and says, would you like to filter it? And it goes and then sends the message to the next layer in the pipeline of the group communication layer, which sends the message across. When a message is received, a similar process happens. It's not delivered immediately to the receiver. It goes through some application module, which goes and returns it back. Further processing happens, and then it's received. Okay. Very quickly, This layer that I've provided could have been implemented using various kinds of IPC mechanisms. I chose RMI. Has the advantage that RMI is very high level, but there's also some disadvantages. So group messages, which is my layer, is different from RMI in that it is multicast, whereas RMI is unicast. But there are also some other differences. Okay, that has caused implementation headaches. And in retrospect, if you read the paper, I would argue that remote procedure call, if it's going to be used ultimately for group communication, should be designed differently than RMI. Okay, and similarly, if it was designed differently, then group messages could have been designed a little differently too, to provide better support. And I think I'm just about making it. My conclusion is that the previous group message tools, communication layer tools, met only this requirement, and it's possible to make.